أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. This is our first online lecture about the course of Introductory Electronics. And if you look toward the lectures series, so this comes as lecture number 13. In today's lecture we will basically discuss bipolar junction transistors, its structures, its operation, and its currents. So the first thing we need to know, or we need to understand in this lecture, is the understanding of bipolar junction transistors structure, the basic structure of that. The second thing what we are intending to learn is the operations of the BJT, that is actually called as bipolar junction transistors. And we also need to know the transistor currents, I mean the various types of currents that is produced during the biasings of the transistors. So the first things is the structure of bipolar junction transistors. So the bipolar junction transistors actually determines its operating characteristics, and it says consists of three different regions, that is called as a emitter, base, and collectors. In one case it have basically two types. One is the NPN and other is the PNP type of transistors. In case of NPN, a P type of extrinsic semiconductor is sandwiched in between two N types of materials. And in the same way, in case of PNP type of BJT transistors, N type of extrinsic semiconductor is sandwiched in between the two P type of materials. So that is why, based on the arrangement of P and N type of materials, there is two types of these transistors, that is NPN and PNP. This is basically the structures of the transistors. Here we have emitter, this is the base region, that is actually in between the emitter and collector, and this is the collector regions. This is the simple structure what we have. In case of NPN, it will be like this. This is the base of the NPN transistors, this is the emitter region, and this is the collector region of the NPN transistor. And this is a sample type of PNP type of transistors. In this case we have P type of material as a collector, N type of material as a base, and P other side, and the P is considered to be the emitter region of this BJT. It is called as bipolar due to the fact that in this case both the holes and electrons are the current carriers, and that is why it is called as a bipolar junction transistor. We have other type of transistors that is also called as field effect transistors, that will come inshallah in the upcoming lectures. In that case only a minority carrier, I mean the majority carrier with the electrons or holes contribute to the current, so that is why that is a type of unipolar junction transistor. But this is actually called as a bipolar junction transistor because at the same time both holes and electrons are considered as a current carriers. So we have different junctions in this type of transistors. Basically there are two junctions in this transistor. One is called as a emitter based junction, another is called as a collector based junction. The PN junction joining the base region and the emitter region is called as base emitter junction, and similarly the PN junction that is joining the base region and the collector region is called as a base collector junction. So a wire lead connects to each of the three regions. These leads are labeled as a emitter, base, and collector. So normally emitter is represented by the letter E, P represent the base, and C represent the collector. So this is again the symbolic representation of the are the structure wise representation of the both PNP and NPN type of transistors. If we are looking toward the doping level or the doping concentration of the different regions of these transistors, then the base region is lightly doped, and if we look toward the size of this region in comparison to the collector and emitter region, so its size is also comparatively small and it is thin. So that is why it is considered to be, maybe in some cases the majority of the carriers can tunnel through these thin regions. So I mean, even the width of this region, I mean the base region, depends upon the doping level. If there is high doping levels, then it will be very thin. If it is lightly doped, so it will be comparatively wide. But anyhow, if in comparison to the P and N type of materials, and also the collector and emitter, if we compare to that, the base is thin compared to that. Looking toward the doping concentration of the emitter region, it is heavily doped, and as size, if we compare to the collector, is a bit smaller than the collector, and in the collector region is moderately doped, and its size is bigger than emitter. So this is the normal configuration of the different regions of the transistor, I mean the base, emitter and the collector regions. So this is the symbolic, the simple representation of the BJT symbols. For in case of NPN, we have type of arrow line. This arrow line point from the base region toward the emitter region. This is the case of NPN transistor. But in case of PNP, if we look toward the arrow bar, so it is coming from emitter toward the base region. So this is the simple representation of the standard BJT. How this BJT operates when it is used in the circuits. So in this slide we will basically discuss the operations of the bipolar junction transistors. So for simple BJT to operate properly as an amplifier, the two, we have actually already discussed that there are two junctions, PN junction in BJT. So the two PN junction must be correctly biased with external DC voltage. So there is different configuration, whether the different junction will be forward bias or it will be reverse bias, but we have specific priorities for each of the junction that will be discussed in the biasing of transistors. But anyhow, if we consider a simple case where the base and emitter junction is forward bias and the base and collector junction is reverse bias, so this sort of configuration is considered to be forward reverse bias configuration, and this is the configuration shown here in the case of NPN type of transistors. It is connected to two sources, one is VBB, another is VCC. So if we look at this circuit into different ways, if we divide that into two different unseparate circuits, so the base emitter region, that comes actually the left side of this slide, that is and similarly the collector and emitter junction, that comes in the right side of this circuit. So if we look toward that, then the emitter leg serves as a conductor for both circuits. So the amount of current flows in the base emitter circuit controls the amount of currents that flows in the collector circuit. So the small changes in the base emitter current yields a large change in the collector current. So that is the most important thing what we are intending to do, that how we can control the magnitude of current. So here if we slightly modify or change the magnitude of current in the base emitter region, so it will leads to huge change in the collector current. So that is what we are intending to do from the operations of the BJT. This is simple operation. How the different junctions are forward and reverse bias. Here we are looking toward the base collector junction, that is reverse bias, and base emitter junction is forward bias. So in that way the current flows. And in case of PNP, if we are considering the same sort of configuration, then this is the base collector junction, that should be reverse bias, and the base emitter junction should be forward bias to carry on such sort of biasings. The heavily doped N-type emitter region has a very thin high density of, it is highly doped, so it will have a high density of conduction bands, free electrons. So these free electrons easily diffuse through the forward bias base emitter junction into the lightly doped and very thin p-type base regions, that is indicated by the arrow, because we already shown in this figure that how did that occur. So the base has a low density of holes, which are the majority carriers, and similarly a small percentage of the total number of free electrons injected into the base region recombine with holes and moves as a valence electrons through the base region and into the emitter regions as a hole current, indicated by the red arrows. Some of the electron will meet with the holes in the base region, that will contribute, or that will lead to the base current. We normally look toward these regions. That is the simple explanation of the BJT and its operations. When the external biasing is applied, so what happens? The electrons that is on this region, that are actually, in case of NPN, we would like to explain the biasing, transistor biasing or operation in case of NPN transistor. This is the N-type region, again this is the N-type region, and this is the P-type region. We connect this transistor in such a way that this is connected to the negative terminal of the battery, again here negative terminal of the battery, P is connected with the positive terminal of the battery, and is connected here with the positive terminal of the battery. So if we look toward this configurations, what happen? This this is a type of forward bias. So the electrons that are drifted in this direction, that is moving. So around 95% of the electron pass through the base, and they are received at the collector, and it contribute to the collector current. So it means 95% of the emitter current is the collector current. That contribute to the collector current. But the 1 to 5% current pass through the base region, and that is create the base current, because some of the electrons are trapped by the holes that is in the base region. They recombine, and that leads to the base current. So the base current normally moves in this direction. So it means with the holes, as a result this mechanism continues, and the base current. So similarly, by controlling the magnitude of base current, we can increase or decrease the magnitude of collector current. So this is the simple operation of BJT. So when the electrons that have recombined with holes in the valence electron, it will lose the crystalline structure of the base, and they become free electrons in the metallic base layer and produce the external base currents. So most of the free electrons that have entered the base do not recombine with holes, because the base is very thin and they pass through that. So as the free electrons move towards the reverse bias base collector junction, so what happens? They are swept across into the collector region by the attraction of the positive collector supply voltage. So the free electron move then through the collector region into the external circuit, and then return into the emitter regions along with the base current. So what happens? The emitter current is slightly greater than the collector current. Part of that emitter current is collected at the collector, so that will contribute to the collector current. So definitely the magnitude of emitter current should be greater than the magnitude of collector current, because part of the emitter current will be utilized as a base current because of the small base current that splits off from the total current injected into the base region from the emitter. So that is why if we look toward the emitter current, it should be the sum of both the base current and the collector current. So this is the simple things. So now we are coming toward the transistor currents, or the magnitude of current that is produced during the biasing of transistors, and how this current is distributed in different ways. What portion contribute to the base current, collector current, and emitter current, and what is the ratio between the magnitude wise ratio between the different part of these currents. So the direction of current in both NPN and PNP transistor and their schematic symbols are shown here in these figures. So we are looking toward the arrow and the emitter of the transistor symbols, that it points in the direction of conventional current. So it is very clear in the case of NPN. The arrow sign basically represents the conventional current. If we are looking toward the NPN transistor, this is the basic structure of NPN transistor. So how the current will flow, because it will flow in this direction. So this arrow line actually describes the direction of conventional current. If we are looking toward the PNP transistor, so the same arrow will be in different directions. So that is why it means that the current will be in different direction. The conventional current will be in different direction. And here we want to elaborate the discussion in the form of equation, that the collector current that should be actually the sum of both, and the emitter current should be actually the sum of both the collector current and base current. So that should be expressed like that, that IE should be equal to IC plus IB. So we are using the same thing, and we are need to know some of the other properties of the BJT when it is used in the circuit. So in this arrangement, some transistors are used when the BJT is used in the circuits. So this figure shows the proper bias arrangement for NPN transistor for active operation as an amplifier, where the same transistor is used as an amplifier. And here it is already clarified that the base emitter junction is forward bias by the voltage source, that is called as a VBB, and similarly the base collector junction is reverse bias by a voltage source, that is called as VCC. So the DC current gain of a transistor is the ratio of the DC collector current to the DC base current IB, and that is called as a DC beta. And we can find out this magnitude. So similarly the ratio of the DC collector current and the ratio between the DC collector current to the DC emitter current is the DC alpha, and its magnitude could be written here. Based on this discussion, we would like to solve an example for the basic understanding of the student, that how they can calculate the magnitude of current, the magnitude of various currents, just like the base current, the collector current, and the emitter current. So we have a simple example of using the same transistor in the circuit. We have the sources like VBB and VCC, and we need to know the beta DC and the emitter current for a transistor. When the base current is given, the magnitude of base current is very, very low. If you look toward the base current is around 50 microampere, and the same collector current is 3.65 ampere. So what we need to calculate? We need to calculate the emitter current. That is very easy, because emitter current is actually the sum of the base current and collector current. And similarly we also need to calculate the beta DC. So let's come toward the next slides, to know and understand the beta DC and emitter current. So first thing, we need to calculate the beta DC, that is actually the ratio between the collector current to the base current. The collector current is 3.65 milliampere and the base current is 50 microampere. If we convert like that, it will be like this value will be we use the same notations, the same units, so it will be like 73. So if we find out the magnitude of emitter current, this is very simple to us. We just need to know the value of the base current and the collector current. So the base current is 3.65 mA and the collector current is 3.6 milliampere and the base current is 50 microampere. So the total magnitude is 3.7 milliampere. So this is the magnitude of emitter current, and in the same way we can calculate the alpha DC, and that is the ratio between IC and the collector current and the emitter current, and we can easily calculate there. So this is something about the transistors and the biasing for the today lectures, and I hope we can move forward in the next lecture about some of other operation of the transistor in the upcoming lecture. Thank you very much.